Good morning and welcome all to today's webinar. I'm Aranza Zugalan, part of the editorial board of BuildUp. BuildUp is Europe's largest international portal for energy efficiency and renewable energy in buildings. It is a unique community that provides the opportunity to discuss, contribute, and collaborate with other experts in this field. BuildUp aims to bring together stakeholders working in the building sector to reap collective intelligence about energy reduction by encouraging knowledge exchange. Our editorial work is organized around a topic of the month, which allows us to go deeper into a specific theme. Each month, several items are produced as overview on technical articles and infographics, but not exclusively. BuildUp also offers the opportunity to host webinars on all the topics related to energy efficiency. More recently, BuildUp has opened the opportunity to distinguished experts in the field to share their knowledge in front of our cameras in the BuildUp Expert Talks. BuildUp portal shares daily the most relevant events in the field of energy efficiency and renewable energy, but also participates actively in many European events around the year as EPV Center and REHVA Conference, Horizon 2020, Interreg and Cost Action events, Covenant of Mayors, and much more, with the aim of further disseminating the results and helping to create high-quality media content. BuildUp content is updated daily, reaching around 120 new items each month. But BuildUp is not only us. BuildUp is a community, and we invite you to be part of it. By becoming a member, you can contribute uploading your own content and promoting your own news, events, or publications. BuildUp will help you to reach a broader audience through our social media channels and newsletter. It is a pleasure to host today's webinar entitled Novel Heat Pump Technologies Based on Natural Refrigerants and Multiple Renewable Sources, which is organized by the REHVA project. Audience is welcome to send us questions through the platform. These questions will be answered at the end of the presentation in a session moderated by Jasper Vermaut, a Policy and Project Officer at REHVA, to whom I leave the floor now. Thank you very much and enjoy.
Thank you very much, Aranza, for the very kind introduction. And indeed, also from our side, a very warm welcome to our webinar, where we will be presenting the novel heat pump technologies that we have been working on within the REHVA project. REHVA stands for Tri-Generation Systems based on heat pumps with natural refrigerants and multiple renewable sources. So indeed, my name is Jasper Vermaut from REHVA, the Federation of European HVAC Associations. And I'll give you a brief introduction into the agenda. The next slide, please. So first, we will start off with a presentation, a quick and efficient presentation by the project coordinator, Dr. Daniel Carbonell from the Institute for Solar Technology, who will give you a nice overview of what has happened within the project, the different, very innovative results. Then we will go on to two presentations that will give you that will explain to you the 3 heat pump systems that have been tested within the project. Then on to how the heat pump system presentation about how the heat pump systems are backed up through an advanced energy management control, which optimizes the energy flows of the different heat pumps. And then at the end, as the last presentation, we will have a presentation on the social aspect, because we've also done research about the social barriers and incentives for the market uptake of heat pumps, which will be presented by Emmanuel Sties. And then in the end, indeed, if you have any questions, you can give us your questions, and we will try to answer them in the Q&A at the end of the presentation. I hope you have a good time during the webinar and you find it interesting. And now I will hand over the floor to our project coordinator, Daniel Carbonell, who will present REHVA in a nutshell.
So, good morning, everyone. So I'm Daniel Carbonell from SPF, the Institute for Solar Technology. We are an institute located in Rapperswil, close to Zurich in Switzerland, and we belong to the University of Applied Science of Eastern Switzerland. So today I will present you the overall concept of the 3HP project. 3HP stands for 3 generation systems based on heat pumps with natural refrigerants and multiple renewable sources. And along this workshop today, we will have different presentations where we will be able to go in details on some of the aspects I'm going to explain and summarize here. Here you can see the logos of our partners. We are 11 partners from 7 different countries. The project was financed within the framework of H2020. It is a research and innovation action, which lets us to move the technology readiness level from 3 to 5, which means that after the project, and this will be in a month and a half, so we are very close to the end, we will be ready to go to the next step and do a pilot and demonstration and bring the technologies to real buildings. The project overall budget is about 5 million euro contribution, and as I said, we are going to finish next month, February 2023. So the main goal of 3HP is to develop what we call 3 generation systems, which are based on electrically driven natural refrigerant heat pumps coupled with photovoltaics. These systems are aiming to provide heating, cooling, and electricity to multifamily residential buildings. Our main targets are to achieve 80% of renewable on-site share with kind of a net zero energy concept. So basically we produce all electricity in our case, because we are heat pump based, that we need over the year, but we need to change 20% with the grid because we are lacking a seasonal storage. And the main developments were meant to reduce cost, installation cost, by up to 10 to 15% compared to current heat pump technologies that would have the same efficiency. And all these would lead to about 75% of greenhouse gas emission reductions with respect to traditional technology that we have today. So in 3HP, we are developing 2 main systems. One is what we call a dual sourcing system, that it's based on the heat pump. So all 3HP developments are centered into the heat pumps and heat exchangers inside the heat pumps, and also into the advanced energy management control and the system integration. Now, in this dual sourcing system, what we have is a heat pump that can use both boreholes and air as sources for providing heating demands, or as sinks for providing cooling demands. And the cost reduction comes from the possibility to use air as a direct heat exchanger or heat exchange within the evaporator or condenser that would allow us to reduce the borehole length by a factor of 2, which reduces significantly the complete cost of the system. All the system is controlled by an advanced energy management system based on model predictive control using variable electricity prices, which is not only able to manage efficiently the heat flows, but also where to store the energies in thermal and also on electrical storages. The next system that we develop is what we call a solarized slurry system, which is a particular case of a solarized system, in which again we have a heat pump as a center piece, but in this case we are not using air or ground as a heat source for the evaporator, but we are using solar thermal energy. Because this solar thermal energy is not always there, we have nights and we have cloudy weeks, especially in Central Europe, then we need something else to provide the heat source, and what we use is a water storage that will ice in winter and be in sensible mode the rest of the year. This system is meant to provide heating demands with some cooling addition, like add-on features, where we can provide free cooling for some periods of the year. And again, we have an advanced energy management system that also manages all the electricity sides of it. Going more into the details of the ice storage, what exists today is what is called an ice on coil or ice on heat exchanger. Here on the bottom, you can see 2 pictures of it. That's storage under construction from company Wisman, that now it's it was done by Isogal at that time. So basically here they are adding tubing all around all the volume. This is under construction, so at the end tubes will be everywhere. And on these tubes, there will be ice growing. So all this storage is of course filled with water. And then this ice layer creates some resistance on the heat transfer. So here, this kind of concept has 2 main problems. One, all these heat exchangers add significantly to the cost. You have to add them everywhere. Plus the efficiency drops when ice grows. And this leads to the fact that the cost scales with the kilowatt hours, so with the energy, the larger the storage, the larger the cost, and this is linear, and not with the power. In order to circumvent all these problems, there is a technology that exists, which is an ice slurry technology. The problem is that what exists commercially in Europe today, it's what is called an ice scrape technology. Basically, in this concept, what you have is a very cold surface that you can see here, where ice builds, and then there is a mechanical device that scrapes ice from the surface. And this is a continuously rotating element that adds complexity, and it increases the capital and operational maintenance costs significantly. And that's why this is not very much widespread. So instead of this, what we propose is what is called a supercooling technology, which is a concept very easy to explain, but quite difficult to implement in practice. Basically, you take water, you cool it down below the melting point by a heat exchanger like this. So it would be 0 degrees, and you keep it in liquid form. So it's in a supercooled, stable form. So you can have water -1, -2, -3 degrees centigrade in liquid form after the heat exchanger that we call supercooler. And then we pass this supercooled water into a device we call crystallizer, and we trigger nucleation in a controlled manner. And then the latent energy is released, forming a mixture of ice and water. And this is what is called an ice slurry. And the difference between this melting and this crystallization point is what we call the supercooling degree. The higher the supercooling degree, the higher the probability of freezing. So what we are developing to avoid that ice forms in this heat exchanger is developing isophobic coatings. The great benefit of the ice slurry storage is that we will have a nice vessel without any heat exchanger inside, which will reduce the cost significantly. Now, in order to develop these two systems, we have to develop the refrigerant cycle and different heat exchangers on it. And we have developed three kinds of heat exchangers. One is this, what we call a supercooler, using isophobic coating. So we develop coatings that were able to delay the formation of ice. And these heat exchangers have been installed in real heat pumps, as we will see later. Another development that has been done is what we call a tripartite gas cooler, which is, a heat exchanger used for efficient domestic hot water and space heat simultaneous production in CO2 transcritical cycles. And the third heat exchanger is what we call a dual sourcing evaporator condenser that is using the dual sourcing heat pump. So these heat exchangers have been implemented in 3 real heat pumps. On the left, you see the dual sourcing heat pump used for heating and cooling. That's a reversible heat pump that's using propane, and also this propane ice slurry heat pump that it's using this supercooler with isophobic coatings. And on the right, you see a CO2 heat pump that it's also using this supercooler with isophobic coatings and the tripartite gas cooler. These heat pumps have been developed and tested experimentally twice. So there were 2 designs. One design where we detected some things to improve, and then there was a second design, and this was tested. And now these heat pumps are being tested and have finalized very recently the testing within the complete system test to see how they would perform with real boundary conditions. And then we have the advanced energy management system. So all these heat pumps together with all the systems and all the storage are managed in an efficient way by a smart control, which aim is to reduce operation costs by up to 15%, and being able to increase the renewable share of renewables up to 80%. And this has been tested on a simulation and also on an experimental base, as you will see in a presentation later on. So I will not take a lot of time explaining this. You will have a full presentation on it. And last but not least, we have done quite a lot of work on technology acceptance. For us, it was important not only to develop technology, but also to make sure that we will not find social barriers in the future that will like impede or will not allow us to implement these technologies in real world. You will also have a specific presentation on it, but there has been quite an effort putting on this, and it's also an important part of the project. So that's it. Hope you will enjoy this workshop. You will get now very nice presentations where you can go in details on different technologies. Thank you very much.
Thank you very much, Danny, for your presentation. And now we will go on to the presentation by Ignacio Gurchaga on the first 2 heat pumps that have been tested within the 3HP project, the propane and CO2 heat pumps combined with the solar ice slurry systems that Danny has just explained briefly already. Ignacio, the floor is yours.
Okay, thank you for your introduction, and welcome everybody who is here attending to this session, to this webinar. My name is Ignacio Gurchaga. and I work also in the Institute of Solar Technology of SPF, yes, in Rapperswil. And the presentation I'm going to do is around the solarized slurry system concept. That is a new system that has been developed, yes, within the framework of the 3HP project. This kind of system, as Danny mentioned before, is a system with combines different technologies: solar thermal, photovoltaics, yes, heat pumps. But the main difference is that we use ice storage as an intermediate storage medium. Yes, so these systems are mainly focused for the European, Central European climate, in order to deliver and supply heating demands as space heating or domestic hot water, and also as an additional feature as a small cooling. Okay, so the difference between those systems and the conventional ones is that heat pump normally uses as a energy source ground, yes, through the boreholes, or air, yes, through the evaporator. And instead of that, the solar isoslurry systems uses only solar energy. Yes, this solar energy feeds an ice storage. Yes, this ice storage is a phase change material, because ice continuously makes this phase change from liquid to solid, from solid to liquid, and has the ability of store a huge amount of energy. But despite this, the amount of energy that we are storing is limited. So the idea is that solar thermal can give energy to those moments, yes, that we have not. Sure. So this energy that from solar thermal can go through the heat pump, through the high storage, or can go directly the solar thermal to the domestic hot water or space heating demands. The main advantage of this kind of systems is that the performance is equal, or even can go further than the ground source heat pump. So we are around space seasonal performance factor between 4 and 5. The target cost is aimed to be the same, yes, despite nowadays we are still prototyping, maybe it's a little bit more, but the idea. And the big point is that is a kind of system that there is it's not necessary to be regenerated. No? Normally, a heat pump that is working with boreholes has to be regenerated, and in this case, there is no need for regeneration. So in order to be able to design these systems, several key developments have been carried out during the 3HP project. As Danny, my colleague Danny mentioned it before, isophobic coatings were necessary in order to avoid nucleation. So in order to avoid the phase change in those parts of the systems that we don't want. So for example, in the evaporators, in the heat exchanger from the evaporators of heat pumps, because if not, we are going to create clogging. So those isophobic coatings were applied to those heat exchangers, that we can see here in the next slide. So from the state of the art, we can see here in this graph that in the reference case we can achieve, yes, minus 2.7 or 8 degrees of supercooling temperature, and with the coatings that are the rest of the bars, green, yellow, and blue, we can achieve almost 4 degrees of supercooling. So the increase, yes, that of supercooling degree that we have achieved within the 3HP project has been an increase quite significant to the state of the previous state of the art. Yes. The second development that was necessary within the project, or not necessary, but could improve, yes, quite much the performance of CO2 heat pumps, was to split the heat exchanger, the condenser heat exchanger of a heat pump. Yes, in this case, we cannot name it condenser because we are not condensing anything. But these gas coolers are split in three. No? Here in the graph, we can see the temperature. There's different temperature levels. In red line is the transcritical CO2 thermodynamic cycle. And here we can see in blue lines, yes, the increase of temperature for domestic hot water, and in green for space heating. So here there is three heat exchanger that are in series, and the 2 and the 3 are for domestic hot water, and the second is for space heating. And this finally, what we can achieve with that is a better performance of the CO2 heat pump that also has been achieved during this project. So for the slurry systems, we have developing mainly 2 systems, yes, that were focused mainly for these Central Europe climates. One is a propane solar ice slurry, and the other a CO2 solar ice slurry system. So it's the same, more or less the same system, but with a different heat pump. Both are natural refrigerants because these are the objectives, the target of the 3HP project. The propane one is more focused for refurbish, yes, buildings, and the CO2 for the new ones that has got a small space heating demand and a huge domestic hot water share. So that's where the 2 targets that were a little bit different for the 2 heat pumps. Those systems were both tested in something that we call concise cycle test. That is a accelerated test. No, is a rapid prototyping of systems that we can make a test of a whole characteristic year in only a few days. So we take in account which are the typical weather conditions of a whole year, and we try to condense it only in a small days. So in a small period of some days. So normally are 5, 7, 10 days that we condense the whole year in order to take in account all the kind of phenomena that we are in the real systems. This kind of systems we can see here in the graph. Part of the system that is in the blue, yes, in the blue box, are real physical installed systems, yes, in our labs. Yes, in this case, we are in SPF, but my colleagues of Technalia and IREC, we are going to explain also the tests in their labs. And part of the system is also is emulated and simulated. So it's not physically there, but it's emulated and simulated. Both systems, yes, were tested in this kind of test, in this concise cycle test. The first one of the whole system was tested in this summer, in June, July. Yes, that was a propane solar ice slurry system. Here we can see in the graphs the heat pump, the domestic and space heating tanks. This system, normally we run it during 1 or 2 weeks, repeating this 7-day period, this 7-day period characteristic of the whole year. So, and then we have to check, yes, the graphs are showing that, which is the 7th period that is thermally in equilibrium. So we check which are the temperatures of the beginning of the period, as we can see here in this graph, and in the end of the period, yes, and check that they are the same. So we check from the day 1 to the 7, from the 2 to the 8, from the 3 to the 9, yes, in order to see which is the period with this thermally stable, yes. And once we check it, yes, we analyze the data. The next graph, yes, we can see which is this data. This graph represents the energy thermal balances of the solar propane ice slurry system. In the positive values are the inputs, yes, that fit the system, and in the negative values are the energy that is supplied, yeah, or outlets of the system. No, here we can see the 7 days, 1, 2, 3, 4, 5, 6, 7. Yes, there are 2 winter days that are days 2 and 3, and 2 summer days that are days 6 and 7. And the days in between are intermediate days of spring or autumn. Yes, we can say, for example, the day 3, that is a typical winter day, when we've got a big bar of light blue color, that is a space heating demand, and okay, also an amount of domestic hot water demand. Yes, this domestic hot water demand is also in the summer days, but in the summer days there is no space heating. So, and this space heating demand in winter, yes, is mainly supplied by the energy of the latent and sensible energy of the ice storage. So here we can see, yes, that this pink column corresponds to this energy that was stored in the ice storage, and also obviously from the consumption of the heat pump that is moving the whole system, okay, mainly. And that's, for example, a typical case of a winter day. And summer days, yes, the energy is delivered directly from the solar, yes, to the domestic hot water. Yes, here we can see it. Only taking into account and also a similar graph, but only focus it in on the ice storage. We can see also here in the day 3 that this energy that we are delivering to the heat pump for producing domestic hot water and space heating comes from the solar. No? The solar charges and discharges continuously. The solar charges continuously the ice storage, while the ice storage is discharged from the heat pump. No? This graph shows this, no? Continually. Here we have got 2 graphs. That's also the first we are seeing the temperature of the ice storage, and the second graph we can see the ice fraction of this ice storage. We can see here that the first day of winter, the day 2, the amount of sensible heat that we've got in the storage goes from 30 degrees, that is the maximum temperature, to 0. Yes. The second day, yes, we are just around 0 degrees. We are mostly the whole day, yes, in ice storage. Also we can see here in these graphs, no, how the second day we have got no ice fraction, almost, only at the end of the day a little bit. But the second day we freeze to 20%. Then we defreeze because the solar goes on, defreezes the system, yes, and then another time at the end of the day we freeze another time, yes, till a 5% this storage, yes, in order to deliver energy to domestic hot water supply, for example. As I mentioned before, the concise cycle test is designed in order that the results are representative of the whole period. So, for example, this was tested as a climate condition of Bern, Switzerland. Yes, so we can say that a system, propane solar ice slurry system, have got a performance around 4.8. Yes, a seasonal performance factor, which is a little bit bigger that normally are designed the ground source with boreholes heat pumps that are around 4 or 4.3. So it's even it goes a step further of the actual technology in performance. So it's a quite good result that we obtained here. For the CO2 solarized slurry system that we finished the test on December, we can see it's more or less the same. What it changes mostly is the heat pump, yes, not only the color, but it's absolutely different because remember this CO2 pump has got this tripartite gas cooler, so it's a little bit different to manage. The seasonal performance factor that we have achieved is as expected between 4 and 5, so that's perfect, but we cannot show the detailed results because we are going through them. But it's very important to see this, that the supercooling conditions, so what we mentioned before, the isophobic coatings and all the key developments that have been made, no, around this project, no, we can achieve, yes, constantly work in supercooling conditions of the heat exchanger. So here we can see in this graph, sorry because it's very large, and so we cannot see the numbers, but the red line belongs to the temperature that goes out from the heat exchanger, and when we cross here this line, we are below 0, so we are -2 degrees during most of 40 hours in continuous way, producing and the heat pump working. So that's a very interesting achievement of the project. So in conclusion, in order not to go through the time that I am allowed, so within the framework of the 3HP project, a new system has been developed. That is a system of solarized slurry. This system has got an equal or even better performance of ground source heat pumps. So even is a system that is not necessary to be regenerated because all the energy comes from the sun, yet despite it's stored in the ice. Several developments have been made that are very interesting, not only for this application but for other. And also that we have been in the cycle test, we have achieved during more than 40 hours continuously supercooling conditions, and also a performance factor of between 4 and 5, which is quite a good achievement. And that's everything. So thank you very much for your attention. And if there is any question, we are here.
Thank you very much, Ignacio. So yeah, we can move right on to the next presentation by Javier Peña from Tecnalia, who have worked on a propane dual source heat pump that's highly efficient. So yeah, we love to hear from you, Javier.
Okay, thank you, Jasper, for your kind introduction, sorry. Yeah, my name is Javier Peña, and I'm working in the thermal department of Tecnalia Research and Development Center. And yeah, I'm going to present you the dual source sink heat pump. I have the table of content in which we are going to see first of all, the concept of the dual source sink heat pump. Afterwards, we are going to see the P&ID and the different components that are approved for propane, because propane, as all of you know, is a flammable refrigerant. So we need some special components and components that are prepared for working with propane. And afterwards, I'm going to present you the results of the experimental campaign with both prototypes. With the first one, in which in heating mode we found some problems, or I mean the performances are a little bit lower than expected. And afterwards, in the second prototype, you are going to see how that behavior was completely optimized. So we are going to see the overall results in cooling mode. I mean, working with cooling. In cooling mode, working with air. Of course, in heating mode as well, with air. And of course, in cooling and heating mode with geothermal, with brine coming from geothermal boreholes. And afterwards, the conclusions. So let me move to the following slide. Okay, here we are. So I'm going to present you a little bit the concept of the, sorry, one upward. Okay, yeah, here we are again. So I'm going to present you more or less the concept of the dual source sink heat pump. At the end, the key component of the dual source sink heat pump is the dual source heat exchanger. As I mentioned, the dual source heat pump works with propane, and the dual source heat exchanger should work as a condenser or evaporator, so should be able to exchange heat with brine or water, or against both. I mean, we can combine both sources or sinks simultaneously. And of course, because of using both sources or sinks, I mean, in winter mode, we are going to avoid the frosting cycles, because we can select in case of frosting temperatures, we are going to have a better temperature in the boreholes, so we are going to select it. So with this heat pump, the frosting cycles are not necessary. So it's an excellent solution for situations in which the heating and cooling demand increase, and there are limitations for the expansion of the geothermal installation and in the number of boreholes. So we can combine not only the geothermal energy, but as well the aerothermal. And as well is a beneficial for heating and cooling networks when integrated as both source or sinks. I mean, for example, compensating unexpected demands, peaks, balancing the system. So afterwards, we are going to see the prototypes that we have developed in the frame of the 3HP project. As can be seen on the left side, we have the first prototype that it was more a test bench for testing the dual source heat exchanger than a compact prototype. But anyway, you can see the dimensions that are the components are quite spread, and the weight. So we have developed a second prototype in order to compact all the components, and of course the dual source as well suffer some changes, and it is compacted as well, and we reduce the propane charge below 2 kilograms, taking into account that is an air water heat pump is close to the market values for the capacity of 12 kilowatts, around 12 kilowatts, in which we are working on. So afterwards, we are going to see the PNID. I have at the beginning 2 slides for that, but anyway, we can see that the components are all prepared for the propane. Of course, the main component, the compressor that is provided by Emerson, the 4-way valves that is provided as well by a company that assures us that it's able to work with propane. The expansion valve provided by Emerson as well, and the wheel of pump, that is the pump that is moving the brine from the geothermal boreholes to the dual source heat exchanger. So and the 4-way valve is provided by Sanwa. Okay, so all the components are prepared for propane, and they fulfill the standard that you can see below. Okay, so we are going to move to the results. We can see as well here the dual source working in air cooling mode, the dual source heat pump. You can see on the crosses that are the results of the first prototype experimental campaign, and the dots are the ones achieved by the second prototype. In cooling mode, as I mentioned, more or less we reproduce on both prototypes the same behavior. I mean, the first prototype works as expected. Of course, at very low compressor speeds, we see some variations in some working points. As you can see, we are working with air at 27 and going to the dual source heat exchanger, and of course the water coming from the return of the space cooling at 12 to our in this case to our evaporator that cools water from 12 to 7. 35 12, I mean air and water going to our heat pump, 46 12 and 35 23. So you can see more or less that in all of the cases we reproduce the result that we achieved in the first campaign with the second, and maybe we enhance a little bit, not only from the point of view of the EER or efficiency, but as well from the point of view of the capacity. So we are going to move to the following working mode, that is going to be the air heating mode. So we are using air as heat source for producing hot water, for space heating, or domestic hot water. So you can see that in that case, the crosses are quite below the dots. I mean, because during the first experimental campaign with the first prototype of the dual source heat exchanger, we have had quite the effect of pressure drop because of the distributor that we have introduced it in order to split the flow rate of propane in each of the circuits of the dual source heat exchanger. So because of that quite huge pressure drop, we have a lower evaporation temperature, and because of that, we achieve lower COPs and capacities. But as you can see, the second experimental campaign, you can see the dots. I mean, the colors are in the same conditions, so you can see the blue arrow and the blue dots. So we can see the enhancement of the reduction of that pressure drop, solving the problem and achieving the values that we expect in the design phase. So we are going to see the following working mode. We are going to move to the geothermal working mode. So in the geothermal working mode, we use the brine coming from the boreholes as heat sink. And you can see as well, as previously explained, that during the first experimental campaign, the values achieved are in agreement with the expected values. And of course, they were reproduced quite close during the second experimental campaign. So this is because when we are working in cooling mode, the dual source heat exchanger is working as a condenser, and in that case we are not working, we are not passing through the distributor, that is the one that caused us the enormous pressure drop in the first experimental campaign, in the first prototype. So working with the dual source as condenser without any distributor, only collectors, the dual source heat exchanger behavior is quite similar during the first and second experimental campaign, and of course the behavior of the dual source heat pump. And finally, we are going to see as well the effect that is reproduced using geothermal boreholes as a heat source. As I explained it previously in the air source heat pump, we can see that during the first experimental campaign, see the arrows or the crosses that we are going that we have a behavior that is lower than expected and lower than the one achieved during the second experimental campaign. We are going to see it in conclusions, but around 15% lower. So during the redesign of the dual source, we avoid mentioning the pressure drop problems. So the evaporation temperature is close to the expected one. We achieve not only from the COP point of view, but from the capacity point of view as well. Better values and in agreement with expected during the design phase. So finally, I'm going to move to the conclusions. I hope that we are here. So as a conclusion, the propane dual source heat pump working at design conditions, I mean at 70 Hertz or revolution per second. I mean the compressor speed. In air water heating mode, in design conditions that air supply at 7 degrees and water supply at 40. in order to produce a temperature jump of 5. We have achieved during the first experimental campaign lower COP and capacity values, but after solving the problem with the mentioned pressure drop of the distributor, we increase it until we increase it 15%, not only the capacity but the COP as well. And on the other hand, in cooling mode, as I mentioned, in cooling air mode, we achieved the results quite similar during the first and second experimental campaign, because as mentioned, we haven't got any problem with the pressure drop in the dual source heat exchanger in that working mode, because the dual source heat exchanger works as condenser. And we have seen as well in the using geothermal boreholes as source, that we have the same problem during the first experimental campaign, and during the second one we have achieved better values, 15% better values, because of avoiding that problem that we found and we solved during the second campaign. So it's the same in the water cooling mode. We achieve quite similar values during the first and the second one, not problems with pressure drops. And I would like to mention as well that, of course, with propane as well, we can achieve, domestic hot water temperatures. We can achieve 70 degrees on the exhaust of the heat pump. Of course, we achieve only 69, but because of the pressure switch, that we can, of course, tune it and put the threshold a little bit higher. So this is more or less all from my side. You are going to see afterwards how this heat pump was experimentally tested in the IREC laboratory and the rest of our processes. So thank you very much. Any question, we will answer it then afterwards.
Yes, indeed. We will, at the end of the webinar, we will have time to answer questions from the audience. Thank you, Javier, for the very interesting presentation. So now we will move on to the Advanced Energy Management Control, which will be presented by Alba Collet from IREC, the Catalunya Institute for Energy Research. I think this is a very interesting part of the project, as it really supports the heat pumps that have been tested and ensures optimal efficiency. So Alba, the floor is yours.
Hi, thanks, Jasper. So as Jasper says, this is Alba from IREC. IREC is the Catalonia Institute for Energy Research that is located in Barcelona. Also, we have a site in Tarragona, and the tests conducted in this project were done in Tarragona. So I will explain the advanced energy management control that we applied within this project to manage the heat pumps. So let me check. Okay, so it changed. So the presentation will be focus on the energy management system. So I will explain a little bit the concept, how the system works, and how we manage all the assets. Then we present some case studies with the heat pumps previously explained by my colleagues. Then the tests and simulations that we did, the results, and finally the conclusions. So when we talk about energy management systems in residential places, basically we face two challenges. The first one is the lack of interoperability of the assets within the household. So, for example, if we talk about self-consumption kits or electrical vehicles or smart meters, each of these devices speaks a different language, what we call in communications protocols. So then it's difficult to manage them because, of course, each of these protocols has its ways to communicate, their own rules. So that's the point. So it's complicated, but the problem also it's increased when we also merge or try to mix that with thermal assets, because there is not existence of this common electrical and thermal management, and this is one of the challenges. Another one is that there are limited possibilities in commercial solutions, so that what we see is that the commercial devices take had some decision trees, and so that the management is done with this not smart let's say decisions. No, it's because there is not a general control. There is some proprietary software that is just managing 2 or 3 devices. For example, the most common one is the inverter, PV, and the battery, but not including the electrical vehicle, and that's all. So there is another point on research here that it's to include more smart decisions in that management. So with the sorry, no, it's going on. I think there is a delay, and maybe I jump 3 or 4 slides. So let me check. I'm trying to go. Yeah. Okay. Sorry. Okay. So what I said regarding the energy management system, we try to cover these 2 challenges, so that this management is an integrated software hardware solution for the smart and dynamic management of the thermal and the electrical part, including the energy building, the battery storage, local generation of PV panels or thermal panels, heat pumps, and that's all. How it or what includes? It includes artificial intelligence, weather forecast, energy market connectivity. So we had price forecast. And with that, what we try is to minimize the electricity costs between 10 and 50%, and then reduce the consumption peaks, minimize the CO2 emissions, and increase the use of renewables. And the thing is that how we do that. Yeah, I click on, but let me check because it's not changing. Yeah, right now. So how we do that? We do that with several modules within the EMS. We have an optimization module that is the one that uses a mixed model predictive control with a 24 hours horizon. It performs an optimization each 15 minutes and sends the commands to a real-time module. This real-time module is the one that is communicating with the different assets and is the one that controls if the decisions on that optimization module could be secure for the different assets. So, for example, just to make a use case is if I have a device and for any reason this device is disconnected, then the real-time module takes into account that and modifies the actions sent by the optimization module in order to have and guarantee the energy balance. There are also two main modules. One is the demand prediction. In that case, it's doing a machine learning module with which predicts the occupancy and the appliances. Let's say it has a forecast of 24 hours about the energy consumption in the building, not only the water demand, but also the electricity and space conditioning. And also we have another module that includes the energy prices and the weather forecast. That it's this module, it's about the external services that provide information to the EMS. For the 3 heat pump project, we had developed 2 special heat pumps to be included in this EMS. The first one is both were explained before, and the first one is the dual source zinc heat pump model, which is reversible, uses propane as natural refrigerant, and we could choose between air and ground source, and it's more adapted to warmer climates. The second one is the solar ice slurry heat pump, also based on natural refrigerants. We had an ice tank as a source. The ice tank is regenerated with solar thermal, and it's more adapted to continental climates. As you could see, these are the simplified models of both these 2 systems. In the case that we study the EMS, we were not only focused on the heat pump, we include in both systems solar PV panels with an electrical storage with a battery. And on both we had heating and cooling demand and water demand and electricity. What we had done is some tests in the laboratory with the dual source. Well, we tested dual source and solar ice. We had done dynamic simulations with computer models for these 2 systems and experiments in the laboratory with real systems for the dual source heat pump and the EMS. Then what we had done is to select typical periods of various consecutive days in winter, summer, and mid-season, and perform the test with that days. To see the behavior of the IMs, if it's good or not, what we have done is to compare that with a reference control those days. That this reference control is the common control that we usually have in buildings, that it's for thermal, it's based on thermostats, and for the electrical part, it's basically a self-consumption. So self-consumption means that with the battery, what we do is to charge the battery with the surplus energy from the generation that in our case is the PV panels, And then when there is no solar generation, what we do is to discharge the battery. And this schedule is repeated each day. And thermostat basically is to stay between a threshold of temperatures. So what we had in the laboratory, it's a mix of real systems and virtual systems. Here we have the real systems. We had a dual source heat pump, 2 different tanks, one for the space conditioning and the other for the water demand. And also we have an inverter with a battery and a electrical grid. So we have here the different photos of the elements in the laboratory. The dual source is within a climate chamber where we control the humidity and the temperature to simulate that we are in winter or summer, depending on the test. And regarding the virtual systems, we had the demands, basically, the domestic hot water demand, the mains water, the space conditioning, PV modules, and household consumption. These virtual systems were modeled in LabVIEW, but I have to explain that also, for example, in the case of the electricity, it's not virtual at all, it's emulation. It means that we charge a profile on the devices, these cabinets that we have here, a power profile, and they follow that power profile. So at least it's a semi-virtual system because we have real power. The EMS controls basically the different elements that are marked with a point here. It decides whether to switch on or switch off the heat pump and to select air or ground source. Also to charge or discharge the battery, to decides on the heat flux, to store energy on the tanks or to consume that in the space conditioning. And so that all these actions are restrictions that we program in the optimization. Regarding the results that we had, here we have the 4-day simulations for a summer case. We have the prices here. The highlighted areas are the high prices. Then we had the battery. In orange, we have the IMs, the EMS results, and in blue, the reference values. As you could see, well, the common, expected schedule in the reference case is, as I said before, this is the midday. So what we do is at first we charge the battery. Positive values means charge and negative means discharge. So we charge the battery at the morning. Then at the afternoon, when there is no sun, we discharge. We repeat this same schedule all the days. And the difference is in the IMs, as you could see. This is not done, so the decisions are a little bit different. So we try to charge the battery not at the beginning. Here, that maybe is when we don't have consumption. So let's see the other results to explain more what's going on. Regarding the heat pump, again, we had the orange, the EMS, and the reference in blue. We could see that in the reference case, we use continuously more or less the heat pump. This is because, well, in this case, it was summer and we need to cool a lot of cooling. So as you could see, more or less, we need this heat pump all the time. In case of the AMs, is not using that much the heat pump, so it's a little bit more conservative, because it has the forecast, so it takes advantage on that. The grid import is the big difference within these two management controls. As we could see with the advanced management system, we had less grid import. So this, of course, has an impact with the cost on the customer or the user, because with these 4 days, we get a decrease in the costs that we at least assume 18%. So seeing that results, we could conclude the economic savings at least at 10%, and the controller uses also the most efficient source, and we had achieved the objective that we had within this project. So that's all.
Thank you very much, Alva. Let's go on to the next presentation, which is looks at the innovations from a different perspective. 3HP tries to take a holistic approach, and we've had quite in-depth research about the social barriers and incentives. So I give the floor to Dr. Emmanuel Stich from the Social Ecological Research in Frankfurt. Emmanuel, the floor is yours.
Hi, Jasper. Thank you for a kind introduction, and warm welcome from my side to everybody in the webinar. So I will present results from a stakeholder analysis, which we did at ESA together with my colleague Thomas Friedrich. Myself, I'm a social scientist working at the Institute for Social Ecological Research in Frankfurt am Main. To give you a short overview on the presentation, just as a background and objective of our analysis, what was the research design, and then different steps of the research design, literature review, results from stakeholder interviews and from national stakeholder workshops, and I will present overall conclusions also at the end. To give you an idea, I mean, you're expert in the field, but there is increasing deployment of heat pumps in most European countries. As you can see, there's numbers for 20, but not see because it's so small, but just an idea about the proportion and numbers of installed and running heat pumps in Europe, all over Europe in 2020. And you see that there are large differences between the different countries. We have in particular a high share of heat pumps in some countries, in particular in the newly construction building sector, but in the existing building sector and in the multifamily buildings, there are much more less heat pumps deployed. So the renovation market is a very interesting and also an important challenge for deployment of heat pumps. Just to give you an example, in Germany, for example, we had in 2021 0.2 million running heat pumps, and the objective of the German government is for the year 2030 is 6 million. So you see there is still a long way to go. So what we did in the analysis, it was on focusing on social acceptance of heat pumps, and we just put the focus specifically on acceptance of market actors. Those are who are in charge, who make decisions around the installation of heat pumps, focusing on market adoption of heat pumps. And we also said that there are different, this is a complex process, there are different stakeholder groups are involved. These are, of course, building owners, but there are also planners, investors, architects, manufacturers, and technical consultants, and also those who are doing the work on the installation. These are installers and plumbers. And we also had a focus on different countries. We had a cross-national perspective from different countries in Europe, focusing on Spain, Germany, Switzerland, and Norway. So the research design was just, we did not do a very, not a representative study, but we started with a literature study to give us some ideas about what are the important issues at stake regarding this acceptance of heat pumps in Europe. Then we did carry out expert interviews with carefully selected representatives of the different stakeholder groups I mentioned a couple of minutes ago, and then just discuss these or fed back these interview results from the interview to expert stakeholder workshops, to key stakeholders, just to give to have their opinion on the findings we had, and then we developed also some recommendations, and these were brought together in a European level stakeholder workshop. So I will go to the results. I mean, from the literature review, you have in Europe generally a broad acceptance of renewable energy technologies. They are well accepted in Europe, but as I already said, market acceptance of heat pumps varies strongly throughout Europe due to different a variety of factors. What is important is that there are, in the literature, we found different categories. Of course, economic aspects, such as economic efficiency or upfront costs, are very important. But we also had a broad literature. We found very much on non-economic barriers or non-economic aspects. For example, practical implementation and feasibility of the system, of heat pump systems, but also more broader psychological, social culture, or organizational aspects. For example, attitudes, mindsets, and also routines, which are among the different stakeholder groups regarding the renewable energy system. So stakeholder interviews we did with representatives, as I already said, from the different groups: building owners, investors, HVAC consultants, planners, manufacturers, installers, architects, and engineers. We had finally 36 interviews, and I give you just an idea of some important results, so that we could say that investment and upfront costs were very often seen as an important aspect and also as an important barrier, but also the simplicity or feasibility of systems and their deployment was also very important issue. And closely related to this, the competence and skills of those who plan and install these systems. And finally, also, of course, public funding and support also as an important issue. In the next step, we organized national stakeholder workshops. The interviews were done in 2020. The national stakeholder workshops in Germany, Switzerland, Spain, and Norway were carried out in June 2021. We have again the representatives of different stakeholder groups, and we had workshops of around 2 or 3 hours, and around 12 persons at each workshop, approximately. But there are some differences between the country. And the result in the workshop, so the participants were invited to share their ideas, their concerns, and also their suggestions regarding the vision of renewable heating and cooling systems in multifamily building with natural refrigerant and heat pumps. What they see, what is important, what would be important to do to deploy these systems in the market. And we also presented results from the interviews regarding challenges, but also regarding supports, maybe incentives that might work. And then we asked the participants of the workshop to rate the challenges. What is the important? What are the most important challenges from their perspective, from their stakeholder perspective, and then to select 1 or 2 of these challenges and to think about what could be solutions, what could be recommendations to overcome these challenges. And I will give you results from this moment. In all 4 workshops, we had as important overall challenge investment and upfront costs. The shortage of skilled workers came up, and also the high planning and coordination efforts, in particular in existing buildings, which are often not so well isolated, which have a heating distribution system, which is not adapted to the which is adapted to fossil energy heat generation and not to heating pumps. And so these are aspects which came up in each of the workshops. And we had also some solutions that have been developed that might be to say that economic efficiency is not only an issue of the upfront cost, but it's also an issue of distribution of costs and benefits between investors and users, for example, is also a perspective of the overall life cycle of the system. And also to do so, there's a need of new business models such as energy contracting or on new finance schemes that makes the distribution of costs viable and attractive for investors. We also had suggestions to simplify systems to provide easy to use planning tools, for example, simplifying systems by using models, a design which looks of heat pumps have components which can be easily put together so that the installers, for example, but also planners can make easy choices and they can easily connect these different components together at the installation site. And also there was a suggestion for new finance and funding schemes. And we also heard that important key actors were building owners, heating installers, for example, in particular, and also planners that would have the power and have the capacity to improve the acceptance and the deployment of heat pumps. Just give you an idea of different topics which came up in the national stakeholder workshops in Germany. For example, there was a training offensive to enhance capacity to install heat pumps as an important issue, but also design guidelines, for example, that make it easier to install heat pumps and to provide planning tools for planners and installers that they can easily choose the right heat pump for the specific condition of the building. In Spain, we had the issue that also global warming potential of refrigerants should be included in the life cycle assessment of heat pumps. And there should also be a broader campaign for awareness raising about benefits of heat pumps. Switzerland, there was more focus on the one hand on planners that they have extra efforts that should be remunerated, or that they might be change in tenancy laws would or a change in tax reduction schemes could make investments in heat pumps more attractive, more appealing for investors. And also in Norway, the issue of global warming potential of refrigerants and the benefits of natural refrigerants and an important issue in the workshop. So finally, conclusions, we can say that there is an increased interest in the uptake of heat pumps all over Europe in different countries, but there's also a need of clear need of policy support that's addressing the lack of skills with installers, for example, by structured training programs which address the different needs in different member states. They have different systems of vocational training, for example, and so you need different programs. Also said that connecting heat pumps to other systems in the building is a complex process which might be made more easily by a modularized construction of heat pumps and components of heat pump systems, but also planning tools. And we have natural refrigerants that on the one hand require additional safety measures in comparison to traditional ones based on HFCs or HFOs, but they have on the other hand benefits that lower ozone depletion potential, they have lower global warming potential. There's lower risk of acidification of water bodies, for example. So it's also made clear that the risks are to the environment or the harms to the environment can be reduced by natural refrigerants. And we see that at the EU level that there should be support for new business models that would allow or support upscaling of existing and developing new supply chains to prevent bottlenecks in production, and also to ensure competitive pricing by new business models like collective purchase or procurement actions of heat pumps. And very important, that we found that there's still, could we say, a mindset which is particularly in the heating sector and the installation business, which is very much shaped by fossil fuels and fossil heat generation. And just to make clear that this comes to an end, it needs clear signals, just as like a roadmap for the phase out of fossil fuel based boilers, combined with a plan for stronger market uptake of alternative solutions such as heat pumps for the different countries in Europe. And also what EU could do with an update on eco-design and energy labeling requirement for heating and cooling systems. This is what I want to share with you. I'm looking forward to. Okay.
Thank you very much, Emmanuel, for the great presentation, and thank you to all presenters. Now we have a little bit of time for, we're going to take 15 to 20 minutes for a little Q&A and roundtable. So if you have any questions, don't hesitate to ask us via the chat, and I will receive them here and ask it to the presenters. Some questions came in already. So I think the first question is mainly directed at Ignacio, which came from the audience. We are currently in major need of new heating systems that will make us independent of fossil fuels. How easy is it to implement the system that we've been working on in 3HP in existing buildings? And what would be the penetration time frame for this?
Okay. The idea of the systems is that quite easy to implement. Okay, because the ISO storage, the ISO slurry storage is quite more easy because you don't need any shape, any form. You can adapt it to whatever. So it's quite easy. So the thing is, we want to make a real demonstration case in a real building in the framework on the next maybe, I don't know, 2, 3, 4 years, yes, in order to continue developing this technology. But the idea is quite easy, yes, to implement it to real buildings because there is no boreholes and no kind of things.
Maybe just to add something, so the solarized systems with the traditional isoncall systems are being deployed already in Switzerland and Germany, so they do exist and they do work. We are providing a solution to decrease cost, and this might take some time to get there, but it will take maybe 4 years, 3 to 4 years to have a pilot and demonstration.
Okay, I think that's very clear in terms of the solar ice slurry system. Then maybe a question directed to Javier about, which brings us back to the core of the project. Basically, we've worked on heat pumps based on natural refrigerants, and we would like to ask you about the role of natural refrigerants. What are the advantages of natural refrigerants in comparison to the synthetic refrigerants that are used in many commercially heat pumps on the market today? What's the difference and what are the advantages?
Yeah, regarding to that, we should look to the past. I mean, in 80-30, around 80-30, the refrigeration starts with the natural refrigerants, ammonia, CO2, hydrocarbons. Afterwards, we move to CFCs and HCFCs because previously people says maybe those natural refrigerants, some of them are dangerous or because the flammability or toxicity in case of ammonia or whatever, but the naturals works perfectly during 100 years or more. Afterwards, all the all the people and all the move to synthetics because of that safety issues. And afterwards, we see that those synthetics affects to the ozone layer, and afterwards, because of that, we move to the HFCs that are the new generation of synthetics. And afterwards, we have seen some years ago that they affects to the global warming potential. I mean, they have global warming potential and they affect to the global warming. So as well, there were some legislations and rules in Europe and the rest of the world in order to avoid those HFCs. Nowadays, we have the HFOs that are the third generation of synthetics. They are not banned nowadays because they haven't got really high global warming potential. But anyway, we have seen in the past that synthetics always carry on a problem to the planet. And afterwards, some analyses are developed and people start saying that the HFOs are decomposed in the atmosphere and they produce TFAs that are a substance that affects the quality of drinkable water. And at the end, it seems that we are going to have another problem for the health. On the other hand, the naturals, they haven't got any effect to the planet or to the health of the people. Of course, they have some problems, but they are affordable. I mean, the CO2 works at high pressures, but nowadays there is not any problem in order to find components in order to work out those pressures. With ammonia, there are developments reducing the charge. That is one of the most important development. I mean, to reduce as much as possible the charge of ammonia in the equipments and systems in order to avoid any risk. Regarding the hydrocarbons as propane, as I mentioned, nowadays there are a lot of components already developed in order to work in a flammable refrigerant atmosphere. And if you prepare the system properly, you are not going to have any problem with that flammability issue. So as conclusion, for me, it's really clear. The naturals are going to maintain and are going to be put future-proof refrigerant. The rest, we don't know. Nowadays, the HFOs, I suspect that in the future, we are going to have a problem. I mentioned some of them regarding those refrigerants and are going to be banned. So they are not future-proof refrigerant, the synthetic ones.
Okay, thank you. So that is well understood. Natural refrigerants have some challenges to them, but on the long term, especially regarding global warmth potential, natural refrigerants are the future. Then another question came in from the audience. I think Daniel, you as project coordinator is best suited to at least start answering this. Were you expecting these outcomes within the project, or is there something that you're looking forward to that varied or that varies, and do you want to improve the performance of it?
So actually, I'm quite surprised of all what we achieved. So in terms of efficiency, I don't think we need to go beyond what we achieve. I would say if future developments of these heat pumps, if we want to bring them to the market, they have to be even, we should work more on simplicity or stability, but not on increasing efficiency. They are very efficient. Supercooling also work excellently. In terms of the supercooling, solar ice system, what we are missing is the development of a crystallizer that we are doing in another projects, and here we were not able, so it was not foreseen to develop this, and it's a scalability thing that we need to cover. But when this is done, we are ready to go to real pilot and demonstration. We don't need to really improve efficiency because it's quite efficient. I don't know, Xavi, in terms of the dual source, if you were expecting this or you were expecting more.
Yeah. As you mentioned, related to the efficiency or the COP or EER of the heat pump, we are quite proud of that. The result that we have achieved are competitive, and and on the other hand, our idea is to install it in a real building and to test it in a real behavior. I mean, during 1 year or more. And I think that we are close to a market solution. And we are working with some manufacturers in order to try to develop something more close to the market in the future.
Okay, thank you for the answers. And we have another question that came in from the audience. I think this is more directed at both Ignacio and Danny regarding the solar ice slurry system. It's from Axel. Is it possible to realize such a heat pump system with slurry ice storage in the order of 100 kilowatts? Or what is currently the maximum performance of the system?
So in terms of scalability, we can scale the heat pump like any other heat pump. We don't see any barrier there because heat exchanger is a plate heat exchanger. We can have of any size. That's not what we are missing currently. It's the scalability of the crystallizer, which is a device that goes after the heat pump. So we supercool water, and then we need to trigger crystallization in a controlled manner. And there we are currently limited in capacity, but we have a couple of projects to scale up this device. But in terms of heat pumps, there is no issue, and in terms of storage, it's empty, so there is no issue either.
Okay, thank you for the clear answer. Now I think maybe a question for Emmanuel on the social side of things. You touched upon it briefly. I mean, you touched upon it that lack of skills was one of the main barriers that came forward to the uptake of heat pumps. And I think this is widely discussed within the Repower EU context in European policy on that is a major barrier for the uptake of heat pumps. During the interviews, what kind of solutions for this barrier came forward from the stakeholders? What was their vision on this particular barrier?
Okay, thank you. That's a very, very important question. One thing we learned is that it's not only the case that there are offers for training, but you have to look at the motivation of installers to use these. And for example, I think it was a suggestion from Norway that training schemes work well if you remunerate the participation of this, because for an installer it is just, say, lost time, because otherwise he or she could do work on the construction side and earn money for this. This is one thing would be important. As I said, the second I think is shift in mindset, is to say, to make clear that there will be a change, that the fossil or that the traditional business model of installers will not work longer, that there is an end to this, and this might be a symbol to say we ban oil and gas, the installation of new oil and gas burners. So this would be work to make this more appealing. And the third one, which came up in some interviews, which might be surprising at this point, is I did not mention this, but if you look at studies about the composition of a workforce in the energy sector in general, but also in the installation sector and the planning sector, there is a very, very few representation of women in these sectors. And it might be interesting because in general, women are very positive towards renewable energies, towards have a positive attitude, but they do not go in this installation and business. So it might be interesting to find out what would we need to make working in this business more appealing for women. That might be a case of work time models, for example. And I think this is a discussion which is very, very in the beginning. This is to how could we make this a very important business appealing for a greater group of a greater share of the population.
Okay, thank you, Manuel. I think that's a very interesting point and very interesting dimension to that we should think about within the industry in the future. Then I think there's another question for Javier that came in. So is sound power the level of is the sound power level of the dual source heat pump comparable to current day A2W heat pumps in the market?
Could you repeat it? I haven't got you.
Is the sound power level of the dual source heat pump comparable to current A2W heat pumps in the market today? So basically, this is about, can you compare the sound power of the heat pump that's been tested to A2W heat pumps?
To air to water, to conventional air to water heat pump.
To conventional water heat pump. Yeah, regarding the capacity, or I mean, yeah, it's scalable. I mean, we can work in the same power level. I mean, regarding the consumption, of course, the dual source heat pump, when works as ground source or sink heat pump, is like a regular water to water heat pump. I mean, you only are going to have the consumption of the compressor, of course, and afterwards the consumption of the pump that is moving the brine through the boreholes. So yeah, of course, when we are working with air source or sink, you need to take into account that you have a fan that normally the consumption of the fan is higher, but having the possibility to move from one source or sink to the other, we have optimized the control in order to obtain the better global COP or EER in each conditions. I mean, maybe there is a temperature difference in between air and ground that should be respected in order to say, okay, so we are going to move from one to the other. Yeah, but there is a delta T in which maybe the global COP is better with the ground, but after that you can move to the air if the difference is yeah, if you achieve some difference in order to obtain a better global COP. So yeah, I think that they're comparable, and I think that you can, of course, work as a water-to-water heat pump, but afterwards you can combine with the air. You can reduce the number of boreholes, or if you want to enhance your system and you have more demand, you can combine it with air. And one last thing, I think that of course the dual source heat pump works as water-water or air-to-water heat pump, but it doesn't mind which is the origin of the water or brine. I mean, you can work as well with PVT panels as heat source. So you are not close to the boreholes. I mean, you are not fixed to work with boreholes. It doesn't mind. It's like a water-to-water or air-to-water heat pump combined in one in a one heat pump. So yeah, I hope that I answered the question of the audience.
Thank you, Javier. Okay, maybe one last question, and then we can round it up to Alva. Similar question to what was asked about the solar ice slurry system before. about the advanced energy management controls. What are the next steps? So currently has been successfully tested on the REHVA systems. Are the plans within IREC to test it on other systems? What are the next steps for the management control?
Yeah, well, thanks. The next steps that we would follow on the roadmap about this energy management system is that up to now, well, we have signed like technology transfer to a company that it's exploiting this management system. But of course, in IREC, what we will is continue doing research on that management. So the idea is to focus on adding new devices to the management system, not only the heat pumps, but also the electrical vehicles that up to now there are well, new features in protocols because it's possible to do V2G and more power to manage. And so this is the thing. Also in the part of markets, there are some things that could be improved and are moving right now. One of them is the flexibility. If we have assets like 3 heat pumps and we can move some kilowatts and do what we call demand response, and so that this is another option and another thing that could be explored within what we call local communities and energy markets.
Thank you very much, Alva. Okay, we've run over time, so I think we have to round up here. Maria, if you could just go to the next slide, I would just say one last thing about our final events. So I strongly encourage you to follow our website and social media very soon, actually this afternoon. You will see promotion appear about our final event if you're interested in the role of refrigerants in heat pumps and the current F-gas regulation negotiations that are currently a hot topic in Brussels. Then we warmly invite you to our final event, which will take place in Brussels on 7 February from 2 to 6 in the afternoon. And it will be live streamed by BuildUp as well, so you'll see it appear on the BuildUp website. With this, I would really like to thank all the speakers today, the 3HP Consortium for the great presentations, and again to BuildUp for hosting us and the good cooperation. Thank you all.
Thank you.
Thank you very much.
Thank you. Bye bye.
Bye bye.
Bye bye.
Apareixerà, Elena, en tots els vídeos.